Greetings, everyone. This video is kind of a review of what we kind of talked about in class today, which is a reflection of using Newton's second law, just drawing some FBDs, doing some practice problems, and just kind of reviewing friction in a bit more detail. All right, so the first half of this is 3 different practice problems, and they all have slightly different variations, but they're all kind of focusing on the same thing. So if you could, we're kind of looking at just the first one, and it says this box is being pulled with 25 newtons of force, but is sitting at rest due to the roughness of the floor. All right, now honestly, here's the deal. These are all practice problems, so what I'm going to do is I'm going to have you kind of take a chance to work through them, unpause the video at any point in time once you're ready, and I'll kind of review how I go through each one. But I'm going to kind of actually talk about the FBDs for each one first, and then kind of talk about how to do the answer to the other questions. So if you could, pause the video, take a chance to kind of work through these things, or kind of see if you agree with what I have on there, and then we'll discuss. All right, so hopefully you had a chance to kind of go through and work these 3 questions. So let's start with the FBDs. The first one says I have a box and I am pulling on it with some force. In this case, it says 25 newtons of force, but the box is not going anywhere. So we know that the box is at rest. All right. Now, because of that, we know a couple things about the forces acting on this object. Because it's at rest, we know it's going at a constant velocity of 0, which means the forces have to be balanced. And if the forces are balanced, that means we got to figure out which ones are kind of balancing out everything. So we start with gravity. We know that there's gravity pulling down on the box. It's not falling through the floor, so there must be a surface force kind of pushing up, supporting it. There's an applied force going to the right. And because it says it is sitting at rest, some force must be kind of going the opposite way to balance out that applied force. In this case, because it says roughness of the floor, we can assume that's friction. All right. Now for the second question. This time, pretty simple. Got a fan cart, I turn it on, there's no friction. All right, so because of this, it says it's speeding up. That tells me the forces need to be unbalanced. And just like we've seen before, we got gravity going down, surface force going up from the track because it's not falling through the track, and then the applied force due to the fan going to the right. Okay, and again, we want to start getting comfortable with this idea. It wants to be second nature to us. We go through when we identify are these balanced or unbalanced forces. We want to make that the first question we ask ourselves when we start to draw our FBDs. All right. Then the third and final question. This fan cart is set to the highest setting and let go. So what I've done is I've actually taken the fan cart and I've basically put it on an incline. And the fan is set so that it's going to push the cart down the hill. So I want to draw the FBD for this one as well. And again, we start looking at what is kind of told to us in the problem. Friction is negligible, so there's no friction. All right. Again, gravity's pulling on it and it pulls straight down. Doesn't matter if it's on a hill or if it's on flat surface. Gravity's always going to pull straight down here. All right. However, the surface force does care about that because the surface force, remember, is always at a right angle to the surface that is exerting it. In this case, because the hill is a little bit angled, the surface force will also now be angled, kind of going up and to the left a little bit. Then there's also going to be an applied force going down the track because the fan is pushing the cart down the track as well. So it's going to look something like this. Now the second piece of this is going to kind of ask you to change something differently, but same deal. Now that we have the FBDs, I want you to go through and answer these 3 questions as well, please. All right? And kind of, again, use what you know about our FBDs. Now that we have FBDs, write out the force conditions. Figure out if they're balanced or unbalanced. If they're unbalanced, figure out kind of what the net force might be, something of that nature. All right? So again, kind of pause the video, kind of work through those. When you're ready, unpause it, and we'll talk about it. All right, so we had a chance to kind of work through these questions. So let's talk about them. So we'll start with the first question for the box being pulled to the right. So it says, figure out the values of all the forces on the FBD. What this means is I want to know how much does each one of these forces equal. All right, well, the first thing you kind of want to do is you probably want to write out your force conditions. All right, and remember, if it's balanced, the balancing conditions mean the up equal the down and the right equal the left. All right, so you'll notice I wrote out my vertical conditions first. My up force is the normal force. My down force is gravity, so Fn is going to equal Fg. I have a formula to calculate Fg, because remember, the weight of an object is just equal to its mass times the gravity be able to 10. So that's 10 times 9.8 newtons per kilogram. You could also do 10 newtons per kilogram if you want to do that as well. But in either case, we calculate the weight. It's 98 newtons, which means the normal force is also 98 newtons. All right. Then the other 2 pieces are slightly easier. We do write down the horizontal conditions. The applied force equals friction because this is balanced. It's not moving at all. And the applied force is told to us in the problem. It's 25 newtons. So because of that, The applied force is 25 newtons. The force of friction is also just going to be 25 newtons as well. And again, we're just using our rules for balanced forces here and using our balancing conditions. The second question with the fan cart speeding up is a little bit different. All right, it's asked us to figure out basically how much force is the fan providing at the max setting. All right, now at first glance it might seem like we don't know enough, but honestly, let's read through the question and it might help us out a little bit. All right, so looking at it, there are a few pieces of information it tells us. It tells me, one, the mass of the cart, and two, it tells me how much the cart is going to accelerate. All right, and by thinking about mass and acceleration, I should start thinking about, I have one of Newton's laws that uses that information. All right, it's Newton's second law of motion. All right, so if I write out Newton's second law of motion, A equals the net force divided by the mass, so the acceleration equals net force divided by mass, we actually can replace a couple of these things with information that we know. We know the mass and we know the acceleration. Now, that means we can solve for the net force acting on the cart, which at first might not seem very useful. However, what's useful here is that if we look kind of at our force conditions, the up and down forces are balanced, so Fn would equal Fg, but there's nothing balancing out the applied force here, that fan force. So the fan force, Fa, is actually equal to the net force because that is the only one. That's actually what is causing it to change its motion. All right? So because of that, if I do F net equals ma, I can rewrite it as Fa equals ma. I know the mass, I know the acceleration. So the applied force of the fan is 0.75 newtons. All right? And again, it might seem like I went through a lot of steps very quickly, but we're just getting used to this idea. We write out our force conditions. All right? If it's balanced, we set the up equal to down, left equal to right. If it's unbalanced, we try to figure out what the net force is and go from there. All right? Then for the final piece, it says imagine I move the cart back. So this is when the cart is on the hill. So imagine that I move it back and I actually change the fan so it's pointing somewhere else. So it's actually now pointing up the slope. All right? Now if we do that, if I point it up the slope now, all right, so that now it's trying to push the fan up the slope, that's going to affect the acceleration of the whole thing because instead of it having the fan pushing it down, actually causing it to speed up faster than it normally would, it's actually going to cause it to either slow down, basically accelerate at a slower rate, or even if it's strong enough, it could actually cause it to start going up the ramp if the fan pushes with enough force. But in either case, it's going to cause the acceleration to change. And in this case, we're going to say the acceleration is going to decrease or might entirely switch directions. All right, but again, we're just getting used to this idea. We're changing, getting used to writing FBDs, and what happens if maybe we just adjust which way a force is going. All right. So right there, this is the first half of the notes. Feel free to pause the video at this point if you kind of want to make sure you can copy down the notes. All right. Now, once you've gone through that, the second half is kind of a quick review of friction. All right. So I'm going to scroll up. For you, it would be opposite, just the way I copied this. I've got a box, and it is at rest on a rough horizontal surface. And what I'm going to do is I'm going to start trying to pull that box to the right. Okay. Now, I'm going to be applying a force over some amount of time, so I'm going to start pulling with more and more and more force. But initially, it's not going to move. All right? Now, what I want you to do is I actually want you to kind of read the questions here, and I want you to answer these three questions where it says basically giving us some things about friction. All this relates back to the video you watched last Friday that talked about friction. This is kind of more of a review for it. But if you're really stuck, get out your friction notes, use that kind of as a guide. All right? So if you could, answer those four questions, and then we'll discuss how we kind of get there. All right? So, kind of look at these different things. The four questions all relate to different rules about friction. All right? And remember, we kind of talked about friction again on Friday, but friction works in two ways. If an object, before you get an object to move, you'll have two surfaces that are basically holding each other together. They won't be allowed to slide against each other. All right? We call that static friction. Now, in order to get something to move, you have to overcome the maximum amount of friction, static friction specifically, a surface can exert. All right? Now, what that means is it tells you in the problem, it says the maximum static friction force is 60 newtons. So in order to get this box to start moving, we're going to have to pull with more than 60 newtons of force. All right? We got to overcome that static friction. The type of friction, we just said it, that occurs before it moves is static friction, because remember, static means not moving. Once it starts to move, however, it no longer experiences static friction. It now experiences something referred to as kinetic friction. Remember, kinetic just basically means movement. So there's two different ways friction is going to work when things are moving. All right? Then for the final piece, this is what is the kinetic coefficient of the friction for the floor? Well, we have a formula to figure out the force of friction. And we already said it's dependent on two things. It's dependent on this weird little symbol that we call mu, which represents the stickiness of the surface, all right, times the surface force, basically how much force the surface is pushing on another force with, all right, and or surface, excuse me. And the reason that matters is because the more two surfaces push together, the more all those little ridges and valleys, if you remember from the video, that kind of get stuck together at a microscopic level, the more they kind of push against each other, all right? Now, we know FFK, we know the kinetic friction force, it told us it's 40 newtons. The normal force, it doesn't explicitly say it first, but if we kind of use our FBDs and we use our knowledge, we know that the up and down forces here appear to be balanced. So the normal force will equal the weight, and the weight is 100 newtons. So right there, you can solve for mu k, it's just going to be 0.4. And the stickiness coefficient of friction, however you want to call it, does not have a unit of measurement. It's just a coefficient. All right? Now, the last piece of this says, in the graph below, sketch the frictional force exerted on the box by the surface as a function of time. All right, well, the first question I asked is actually, at what time does the box begin to move? Now, these two graphs that are kind of next to it, one is filled out, one is blank. The one on the left is actually just measuring how much force I am pulling on the box with, me personally. All right, now, the box to the right is actually measuring the amount of friction the box is experiencing. And you'll notice if you look at my graphs, for the first 3 seconds, they look exactly the same, all right? But at 3 seconds, a very important thing happens, and that is that the graph on the left, the graph measuring how much force I pull with, reaches 60 newtons, which means as soon as 3 seconds passes, I'm now pulling with more than 60 newtons of force. So I've overcome static friction, and the box is now going to start sliding and only experiencing kinetic friction, all right? Now, because of that, kinetic friction we've already talked about is a consistent value. It's constant. So to show that, I draw a horizontal line right here at 40 newtons for the rest of the time to signify that the force of friction has now changed. All right? So these are just kind of two brief reviews about Newton's second law and also using kind of friction in more detail. If you have any questions, please don't hesitate to come to office hours or shoot me an email. Otherwise, have a great rest of the day, y'all.